Welcome back to the series of PLL lectures. So this is third lecture in the series. In this lecture, we will go through AC modeling of all the PLL blocks we discussed. Finally, we will model the PLL as a whole block, and we'll see the AC response of the system. Why we are doing this is whatever we have discussed in last lecture, these all equations, closed loop equations, open loop equations, these are just linear equations. But when it comes to actual system, we need to model the system before going to transistor level designs. So here we will discuss the actual modeling of those blocks, and we'll see its response, basically response in terms of phase margin and bandwidth and gain. So whatever we have finalized, let's rediscuss those things. So in last lecture, we came to conclusion. What was that? So we were using a reference. Okay, let me copy the full PLL block. Yeah, so this was our full PLL block. Copy it here. So this was our full PLL block. So for which we have summarized some parameters. I will copy these things also. Sorry for this things. Okay. So this was our PLL block, and these were parameters which we have finalized. Okay, it came like this. It's okay. So what we have decided is FREF should be 25 megahertz. I hope it's visible. Okay. So what we have decided is reference input to the clock is a 25 megahertz input. Then what we are targeting is output frequency to be 2 gigahertz. So basically, we are designing our PLL for 2 gigahertz of frequency. So since reference clock is 25 megahertz, and we are designing this PLL for output clock of 2 gigahertz, so the divisor ratio will be 80, basically 22 gigahertz divided by 25 megahertz. So if you will do like this, so divider ratio of frequency was n equal to 2 giga by 25 mega, which is nothing but 80. So basically, what we will fix in our AC analysis is we will model each block with respect to its gain. How gain? So this n we have decided in last class was 30. This was decided to be 25 megahertz for our design, and this was 2 giga. So basically, we are designing the PLL for 2 gigahertz frequency. Okay. Again, we have modeled this TFD and charge pump together, and we came to a ICP as per our last discussion. We have calculated ICP based on the equations to be somewhere around, what is that? 39 points. So basically, I'm just summarizing all the parameters which we will use in this series for modeling our PLL. So ICP we have modeled it for 39 point, basically 39 point. I messing it up. 39.4 micro amps. So this 39.4 microamps. Then we have also decided resistance and capacitance of this loop fast filter, which was nothing but 8.92 kilo ohms and 20 picofarads. Again, we have decided the KVC of this VC also, which was nothing but I think I've written it in gigahertz per, but if we'll go in terms of frequency, okay, I think this for So as we have discussed in last class, but I will again uh, do this KVCO thing, how we got KVCO. So basically, we are designing our PLL for 2 gigahertz of frequency. What so we can tell like FC equal to 2 gigahertz. Okay. Then we wanted since our supply is 1.8, so we are keeping a center the control voltage a safe margin of zero point 0.9 volts for control voltage. Then we have assumed some upper limit and lower limit for frequencies, which is FH and FL. So plus minus some 5%, 25% it will take. So FH will be means higher range 2 gigahertz plus 25% will be some 2.5 gigahertz. Then FL will be 2 gigahertz minus some 5% of 2 gigahertz. It will be somewhere around 1.5 giga. Then VH will be zero point 0.9 plus 25%, it will become 1.1. Then VL will be, lower limit will be zero point 0.7. Okay, so what was K ratio then? For a 25% of limit, K ratio is basically FH minus FL. FH, sorry for bad handwriting. FH minus FL divided by VH minus VL. Okay, which is nothing but 2.5 giga. Okay, what is units for this? Gigahertz per volt. Hertz per volt. Unit of kVc. So for our design or modeling, we are considering kVc as 2.5 giga. So now I think mostly I have discussed all this block. So now we'll directly jump into cadence and we will design our blocks or we'll model our PLL blocks. Okay. So basically I have already opened cadence. We'll open a new cell view. Okay. If you guys are new, okay. I am hoping that you guys know how to make a library in Cadence. If you don't know, you can search any online content and you will be able to know. So I have made already a library called PLL using GPDK90 technology, and in that library, I am going to use my AC model. Okay, AC model. Oh, okay, okay. Something happened. Why this came? Okay, again I'll make some new cell view. AC model, okay. View I have to select as schematic. Okay. I hope my screen is visible to all of you. So here what we'll do first, basically every design have one supply and one ground. Okay. Okay. So we will keep it as DC voltage of VCC. Then We'll we'll do a DC voltage of 0 for ground. Okay. Then we'll select a VCVS. VCVS. Okay. Yeah. Yes, we are going to use again. We'll do. Uh, okay. Okay. I should explain also. Just give me some time. I will arrange all the blocks and then we'll come to. Okay. Okay. I think I have already made one model. We'll go to directly that model. So this is the AC model which we are going to simulate. So I will explain block by block how I have modeled. As I already explained, these two are supplies. One is DC supply, one is ground supply. Okay. So first block is nothing but PFD. I have modeled PFD just like a. Okay. So how we are modeling here? So why we model? We are model just to get close as the actual model response. That's why we do modeling of blocks. Before going to actual transistor level design, we will do modeling. So how we are modeling here, we are modeling with respect to AC response and we'll see the AC response of our block. So first block was PFD. So how again, so why how our PLL works in basically frequency and phase domain, but actually in cadence we don't have that thing to utilize. So what we have modeled here is so for frequency we are taking current sources, and for phase we are modeling it as voltage source. Okay, so so first block is PFD, so that's why we have used a voltage controlled voltage source to model PFD. So PFD is modeled like this. So basically I am using a open loop as we have already learned in the last session, this open loop characteristics. Is that yeah, so this was our final open loop characteristic K into 1 SRC by SS square after taking effect of each of the term, that is ICP by 2 pi, then 1 ICP by 2 pi for PFD plus charge pump together, then low pass filter 1 plus SRC1 by SC1, then KVCO by S for VCO, and 1 by N for frequency divider. Okay, cool. Let's go to each of these blocks. So KVCO plus charge pump. So this is PFD plus charge pump, which both we are modeled by ICP by 2 pi. So actually to get a feel of PFD, we have added this voltage divider also with a EGAN of 1, and I have given this actual charge pump, which is nothing but a voltage controlled current source. So what I have used is ICP by 2 pi. 2 pi is basically 6.28. So this is how I model charge pump. Then loop pass filter with a resistor and capacitor. And again, after this, our main VCO, there is two inputs, center and the control. So center is basically 0.8 which is safe margin, and control voltage, which is current from loop filter. So after this, again to get this voltage current into voltage, which is actually the output phase. We have added one extra capacitor of 1 farad, basically very high farad. This is only for modeling our VCO block. Why we are using this is to convert this VCO current into voltage. Because actually why we are doing this to get a phase output. So this capacitor will basically store the current in terms of voltage. So as I already told, for modeling phase we are using voltage, and for modeling frequency we are using current. And this stage is again feedback to frequency divider. So again, so this for gain of this VCO block, I have used 6.28 into KVCO as we have discussed. Oh, why we are using this 6.28? Because, okay, let's go into this. Last time we have discussed this KVCO by S. So when we'll go in terms of frequency, and we'll balance the units. In that case, we will add one more hook item. Again, how it is coming is this ICP by okay, this ICP by 2 pi will have a unit in terms of ampere per radian, and this is something in hertz, kVco by S. So to balance these two, we will multiply with 2 pi term in KBCO. That's what we have done in this module. So basically, we have multiplied by KBCO into 2 pi to get the gain of VCO. Again, the frequency divider gain is 1 by n. That we have already discussed because it is dividing by 1. So all these things are now ready. Now what we'll do, we'll launch ADXL. ADXL will launch. I think I've already opened ADXL tab. So ADXL tab is there. So what I have done is here we'll go to add analysis, and there we'll add stability analysis and frequency, and we'll see frequency from 10 to 10 hertz to 10 gigahertz. We'll do logarithmic slope, and points per decade will be 20. Again, how we have opened the loop here. Okay, let's discuss this. So, first, this was our AC model. So we have added voltage source here, and we are opening a loop with, for any stability kind of stability. As you guys know, you should open the loop and then calculate the open loop characteristics of PLL. So for that, we are using this voltage source to open the loop, and that's what we have added in this analysis. Okay, so this is done. After adding that, what we will do, we will add this to output, this to the output. How we have added that? Okay, this is the so when we run this, so this you can remove. Okay, then something happened. Okay, so now what I have done is, so this AC analysis is already added. So here, we whatever variables we have chosen, if we do copies from Cherry, it will all these variables will come. Then we have put okay. I have modified cap and ICP value. Other than this, I have kept it all the same. Why I have modified it to achieve my desired value that I will explain after this setup explanation. Again, in outputs, we will lotte, select on schematic. So, we have added this feedback clock here. Why we have added feedback clock is this. So basically, we are feeding from here, and we want this output. We want AC response of this output. So okay. Again, after this, if you open, you can see loop gain phase. All this we have added using stability analysis, not which we will see just now. So if I will run this, Okay. So if you will go, so you won't get these things. I, I, I think I'm not able to finish all these four things, but you will get this web form, feedback log. So when you right click direct plot, main form, then we'll go here, you will get these kind of add to outputs. So you can add to output or plot also. So you'll get a phase response and end response. Here if you will see, okay, this also I have not discussed. So let's discuss this. This plot we can discuss. This plot we will discuss in detail here. Uh, so basically, what is this open loop function? This is a two-pole system. Okay, this is a two-pole system. So how the phase response or magnitude response at any two-pole system will look like? So magnitude response, let's start. So basically, this is a two-pole system. So it will start with minus 40 degrees of dB per hertz. Means, so it will be minus 40. And then there is a pole also. After that, it will settle for some time because of the pole, and then again it will drop with the slope of minus 20. So this is how our basic magnitude response should look. Okay, suppose the zeros are here. So how our phase response will look? Our phase response will start from minus 180 and it will give a minus 45 at the zero, and then it will drop to minus 90. This is how our phase response should look. Then, okay, one more thing I wanted to explain. Just for recap, since I will get it for that. So what is gain margin, phase margin, and phase crossover frequency? So gain crossover frequency is the point where we are getting a 0 degree of gain. Phase crossover frequency is the frequency where we are getting 180 degree of phase. So what is gain margin? At phase crossover frequency, from DC gain, how much offset is there? So this is minus 20 dB. Basically, it should be greater than 1. Gain margin should be greater than 1 for a gain stability. Again, what is phase margin? Phase margin at gain crossover frequency, how far is the phase from minus 180 degree? So basically, this is minus 9, which is again unstable. For stability, the phase margin should be above 45 degree and best or better stability. For better stability, it should be basically greater than 60 degrees. That's what we have learned in our basic control system classes. So we'll go again to this. So we have what we can do. One thing is we will take this. We can to calculate to calculate phase margin. Calculate. Okay, I have already done something. You doing this. Send to calculate. And basically we are calculating phase margin. Okay, you can show this number. Phase margin. Okay. So you will calculate. You are getting this. Okay. Yeah, we'll go to our terminal again. So when we'll calculate, uh, so this we have added from calculator to here. So we are getting a phase margin of 67.75, which is desired, and the phase margin frequency is 1.206. So how we got it? Basically, we have then some of that. This also you need to explore. Uh, so basically, in last class, what was our target? Bandwidth was 1.25 megahertz. How we got this 1.25? Reference frequency by 20. For this is rule of thumb for any PLL design. Okay, so that's why we have selected 1.25 megahertz. But since we didn't got 1.25 megahertz, we have tweaked some value. So this was the bandwidth formula from the last class by comparing the standard equation and closed loop system. So we got bandwidth equal to ICT into KVCO divided by 2 pi L into C1. So if we reduce ICT, and basically after first cut run, I was getting some more phase margin frequency that is our derived bandwidth. So what I have done is I have tweaked the cap and ICP. So I have reduced the cap value and increased C1 to get our desired bandwidth. So after I have used cap value is 35, but in our hand calculation we have got okay, this was the table, right? What we got was 20. So I increased the cap value from 20 to 35. And the ICP what we were getting was 39.4. I have reduced it to somewhere around 26 in our design. So by tweaking these two values, we were able to get our bandwidth near to 1.25 megahertz. So this was the overall AC response analysis of PLL law. Stay tuned. We'll get back into. We'll use these values to get our transient module. Thank you. Thank you so much for watching.
Free audio post production by alphonic.com.